Good evening, everybody. I really must rewrite my biog on my webpage, I think, after that one. Firstly, it's fantastic to see so many people here for this event. These are great events that have been run by the RSC, very regular kind of events to celebrate chemistry. And we all live in the challenge of trying to widen participation in science. So it's always great to see so many people and such a diverse range of people here for this event this evening. Whether or not we can all make it along for the Hitchhiker's Guide to the Galaxy, which sounds even more exciting, I don't know. Just to remind you a little bit what Lucy says, is the RSC are running a series of public lectures in and around water. There was one a couple of weeks ago, which looked at water distribution from the Roman time and forward. And if you're interested in water as a topic, that's still available up on the RSC website as a webcast. And it's well worth a look. The next event is, as Lucy said, is on the 2nd of June. And this is going to be looking at water sustainability, both municipal water usage, but also food, agricultural usage, and a global perspective on that. And Richard Allen's an excellent speaker for that. So, we're here to talk about water tonight, and water is a fascinating subject. I see a lot of you sitting here with the Evening Standard, and if you look in there, there's articles about water in there. If you look in this month's Chemistry World, there's a number of articles covering a whole plethora of interests associated with water. Now, water is a very fascinating topic that we all think we understand and know a little bit about. So therefore, I'm delighted to be invited to come along to the event tonight and to introduce Philip, our speaker for this evening. Most of you will recognise Philip from his monthly opinion piece in the Chemistry World. One of the articles we all read and enjoy. And this month's one is a very interesting one, which does pick up on the topic of water. Following a long career in working for Nature, Philip now works as a freelance science writer and has written many well-known popular science books, including one on water called H2O, A Biography of Water. So he's an ideal candidate to talk to us about water tonight. While having a look on his website for a bit of information ahead of this event tonight, and I'd suggest everybody has a look to get a big, deeper understanding of Philip's background. He wrote an article in Nature on how to keep drying water. So he's very good at getting the titles of his articles to capture knowledge. So he wrote this article on how to keep drying water, which states that water is notorious for behaving strangely. And given that his title tonight is Why Water is Weird, I think we're all about to learn much more about water and its unique role in life on Earth. So I'd like to welcome Philip.
Thank you, Simon. Thank you, everyone, for coming along tonight. Yes, I was at Nature for a long time. I joined, actually, in 1988. And when I did so, I had just completed a doctoral thesis in liquid state physics, but I didn't expect that to be at all relevant to anything I'd have to deal with at Nature. I was proved wrong even before I started work there, because just weeks before that happened, Nature published a paper which is now infamous, and which claimed that water has a memory. And the authors of this paper, the French immunologist Jacques Benveniste and his colleagues, reported that they found biological activity in solutions of antibodies diluted to the point where there should be no molecules remaining at all. Stranger still, this activity seemed to appear and disappear, to sort of rise and fall as the dilution progressed. Now, at face value, this phenomenon seemed to have no plausible explanation according to the known principles of chemistry. If you don't have any molecules, then they shouldn't have any effect. But Benveniste and his colleagues did think they had an explanation for what was going on. They said this. They said water could act as a template for the molecule. For example, by an infinite hydrogen-bonded network of, or electric and magnetic fields. What on earth does that mean? Well, it will become clear shortly what they thought it might mean, but let me confess right now that I think this is actually probably one of the least meaningful sentences that Nature has ever published. Or rather, the meaning is not in the words, but in what lies behind them. I want to give you an indication of what lies behind them. So Benveniste and his colleagues have found a way of alluding to the peculiar chemical character of liquid water in a way that sounded plausible and scientific enough to pass beneath the radar screen of the referees, who I suspect had no real knowledge of liquid state theory. What they had done was to capitalize on the unquestionable weirdness of water. Now, they weren't by any means the first or the last to do so, but let me just remind you how this particular story played out. As you can no doubt see immediately, Benveniste's paper seemed to offer support for the claims of homeopathy, that solutions diluted beyond the point at which any active ingredient remains nevertheless have physiological effects. And for this reason, the paper became not just highly controversial, but very politicized. After Nature published it, the editor, John Maddox, at that time, led a team on a visit to Benveniste's labs, where they watched over an attempt to replicate the results. And the researchers proved unable to do this, to demonstrate the same rise and fall of biological activity as dilution increased. And Maddox's investigative team pronounced the previous findings a delusion. Benveniste called this a witch hunt, and he persisted with his high dilution work, and this culminated in what he called digital biology, whereby he claimed to be able to use electromagnetic signals to send biological activity, in effect, down a telephone wire, and to use this to program pure water to act as a vehicle for that biological information. And he pursued that work until his death in 2004. And there are still some today who swear that something like the memory of water can cause high dilution activity or something like it. Among them, incidentally, the Nobel laureate immunologist Luc Montagnier. Now, this wasn't an isolated episode in the of strange claims about the properties of water. Most famously, there was the polywater scandal of the late 1960s, where Soviet chemists claimed to have isolated a new form of water in very narrow glass capillary tubes, which had the consistency of soft wax. And it was even suggested at that time that this might turn out to be the most stable form of water at everyday temperatures and pressures. And so the fear was raised that a globule of this polywater dropped into the oceans might cause the whole oceans to gum up. Rather as the fictitious Ice Nine froze all of the world's seas in Kurt Vonnegut's novel Cat's Cradle. Yet it turned out that polywater was actually just another delusion, that it was this waxy stuff was, it seemed, a concentrate of impurities, most probably silicates leached from the glass. Incidentally, Vonnegut's Ice Nine was discovered in his book by a scientist named Felix Honecker, who was apparently modeled on the American scientist Irving Langmuir. And it was Langmuir who coined the term that is now commonly used to describe both polywater and the memory of water. Langmuir said these were pathological science. Well, water has a remarkable ability to attract pathological science. Sometimes this leaks out into the pages of the regular scientific literature. On other occasions, it remains very much at the fringes, where science blends into mysticism. As, for example, in the extraordinary story, and it really is an intriguing story, of the Austrian forest warden, Victor Schauberger, who had ideas about what he called living water energized by vortices. And these ideas were allegedly harnessed by the Nazis, who forced Schauberger to try to develop some secret weapon for them based on his idea of implosions caused by these vortices. So this is really an area where New Age mysticism blends into technological reality. I've heard other scientists, serious scientists, swear that magnets really can descale kettles, and that specially treated metal rods can alter the taste and viscosity of water if you use them to stir it. And I've discovered that if you tell non-scientists that you're interested in the properties of water, then it won't be very long before someone mentions the work of Masaru Emoto, who apparently changes the shape of snowflakes with prayer. And he had a best-selling book explaining how he did that. And this, is, for example, is a sample of frozen water taken from a lake at Fujiwara Dam in Japan. And it's described by Emoto as dark and amorphous with no crystalline formations. But then it's treated for 1 hour by being prayed for by a chief priest of the Juhoin temple. And now then new samples were withdrawn from that water, and it formed crystals looking like this. And apparently music makes its influence felt too in Emoto's work. So when water was crystallized after being exposed to Elvis Presley's Heartbreak Hotel, the crystals are reported to have spontaneously broken into two, which is rather sweet. Now, what is going on here? Why does water attract this weirdness? Well, one reason, which I think scientists rarely appreciate, is that studying water isn't like studying most substances. It's not a neutral subject. All of us bring to it a wealth of cultural associations that are probably impossible to put aside. Water is an element, not, of course, in the chemical sense, but in the mythical and poetic sense, and that's not irrelevant. I'd recommend to you a book by the French philosopher Gaston Bachelard called Water and Dreams, in which he explores the various poetic incarnations of water that have deep roots in myth and legend. And I believe that ideas like this, ideas of water as a purifier or water as a saviour, that they lay unconsciously behind some of the pathological episodes of water science. But there's more to water's propensity to spawn pathological science than its centrality in culture, because the fact is, the water really is weird. And what I mean by that is that water isn't like other liquids, or at least not like the kinds of liquids that one tends to study as a liquid state physicist. It might seem perverse to outsiders that I spent most of my PhD considering liquids like liquid argon and liquid nitrogen, which most people will never see, and which don't exist at all under ambient conditions. But the fact is that those liquids are easy to understand, and to make simple models of them, you can think of them basically as just hard molecular spheres or atomic spheres that are weakly attracting to one another. Water is different, and you can tell that it's different straight away, for example, by comparing it with other chemical compounds of a similar constitution. So water is the hydride of oxygen. It's an oxygen atom with two hydrogens attached. Now, if you compare it to the hydrides of other elements in the same region of oxygen in the periodic table, then you'll see that you'll be comparing it to substances like methane and ammonia, hydrogen fluoride, hydrogen sulfide, hydrogen chloride, all of which are gaseous at room temperature. Hydrogen fluoride just about, certainly in the summer. They're all gaseous. And yet water, for some reason, isn't. It seems to have a much higher boiling point than these. And then there's ice. Ice floats. And that's so familiar a fact that it's easy to forget that almost every other substance we know of gets denser when it freezes, so the solid should sink. Ice, in contrast, expands when it freezes, and that, of course, is why frozen pipes burst in winter and why the Titanic sank. But it's even stranger than that, because ice doesn't suddenly expand when it freezes. It actually begins to expand slightly before that. It begins to expand once it's cooled below 4 degrees centigrade. So you see here's a plot of the density against the temperature, and it has its highest density at 4 degrees. And then as it cools below that, it starts to expand, and then there's this big jump when it freezes. For this reason, the bottom of a lake in winter is actually slightly warmer than the top. It's the densest stuff. And it's also this reason that, and that's why lakes freeze from the top down. And that prevents some of them from freezing solid in winter, since this surface cap of ice insulates the water below. And these are just some of the most obvious and easily understood of a whole list of so-called anomalies of water. Now, happily, just about all of them can be explained with a single fact, which is what distinguishes water from the simple liquids like liquid argon. And this is that water molecules have a certain stickiness for one another because they can form weak chemical bonds called hydrogen bonds. Now, the conventional explanation for hydrogen bonds goes like this. The oxygen atoms tend to draw towards themselves the electron cloud that binds it to the hydrogen atoms, and this leaves the hydrogens with a slight positive charge. And moreover, the oxygen atoms have two pairs of electrons which don't take part in chemical bonding and which sort of stick out in lobes at the back. And so the hydrogen ions are electrostatically attracted to these lone pairs, these areas of negative charge. And this attraction is what causes the hydrogen bond. Now, this is actually too simplistic a picture, and in fact, we still don't fully understand how to describe hydrogen bonds. A committee for the International Union of Pure and Applied Chemistry, IUPAC, is right now working on a completely new definition of the hydrogen bond that will take account all that we have learned about it in recent years. But it'll do as a crude description. Now, hydrogen bonding isn't unique to water. In fact, several other simple hydrides form hydrogen bonds, including ammonia and hydrogen fluoride, which is why they too have slightly higher boiling points than you might expect. But in water, every molecule can form no fewer than 4 hydrogen bonds to other molecules, 2 via the hydrogen atoms and 2 via these 2 lone pairs of electrons. And what's more, these bonds point in particular directions in space. So you can think of a water molecule as a kind of little being with 2 hands representing the hydrogen atoms, which tend to grasp hold of the 2 ankles representing the lone pairs. So you can sort of imitate a water molecule by doing this. That's the kind of shape. Okay, and once those link up, those arms grasp ankles, then you get this sort of structure. And so you get each water molecule has an essentially tetrahedral arrangement of other molecules around it. And this is a 3-dimensional structure which just repeats and repeats again and again in space and creates an extended network throughout all of space, which I've shown in these 2 different ways here. Now, because of this network, there's a tension between the usual tendency for molecules in liquids to jostle up close to each other and the requirement for water molecules to be kept, as it were, at arm's length in order to form these hydrogen bonds. And these bonds can bend and deform a little bit, but if they bend too much, then they'll break. And the key to water's oddness is this delicate balance between the dense, random packing of molecules and the more open, orderly arrangement of this tetrahedral hydrogen-bonded network. Now, in ice, the regularity of this network is rigidly imposed, and so ice has this kind of structure where you get complete order, and this explains, and by imposing this structure, you can see there's actually quite a lot of empty space here, and that's exactly why ice has this, why it expands, why water expands when it forms ice. And it also explains why there are so many different crystalline forms of ice. There are about 12 at the last count, which appear as ice is squeezed at different temperatures. Because with all of that space, the water molecules can find different ways of packing together. And in particular, they can pack together more closely by forming a second network of hydrogen bond, a second hydrogen bonded network in the gaps. Now here's a picture that sort of represents how this happens. So here's one that's representing, just very schematically, they're not actually really like this, the 6-membered rings of that ice network. So if on this dance floor where they're forming, the dancers are forming these hexagons, if we suddenly give them less space by packing more chairs in, then they can, the same number of them can occupy a smaller volume of space by overlapping the rings. And that's essentially what's happening in some of these high pressure forms of ice. So there really is an ice 9. There's an ice 10, 11 and 12 as well, but it's not exactly the ice 9 that Kurt Vonnegut imagined. But there are other forms of ice as well that do remain solid above 0 degrees centigrade, like the fictional ice 9 did, but only so long as they're kept under high pressure. Here's one of them. This is ice 7, and here the 2 different networks, or the 2 hydrogen bonded networks that are interwoven, are shown in red and orange. Now, when ice melts, some of these bonds are broken and the molecules can then come closer together, and that increases the density. And the hydrogen bonded network in the liquid is therefore highly imperfect and disorderly and also dynamic. The hydrogen bonds between the molecules are constantly being made and broken, so that each of them lasts on average just a picosecond, just a trillionth of a second. And physicists and chemists working on water have long struggled to find the best way of describing that network with its intimate blend of order and disorder. And it seems clear that each water molecule has this roughly tetrahedral coordination, but because of all the broken bonds, they have on average less than 4 bonds each. And whereas in ice, the hydrogen bonds link mostly into, well, link entirely into 6-membered rings, in liquid water, it's more common to find 5-membered rings instead. And what's more, some water molecules actually have more than 4 hydrogen bonds because they can form so-called bifurcated bonds in which one hydrogen atom links to 2 oxygens. I should mention that even this average structure of ordinary liquid water isn't fully settled. Some scientists have recently claimed that water molecules can be linked, are linked into, in the liquid state, the normal liquid state, into long chain-like structures rather than this 3-dimensional network, or that there are subpopulations of water molecules, some in chains and some more densely packed. Another proposal is that the structure of water is more like a mixture of patches of something rather ice-like and regular, interspersed in a more disorderly jumble of molecules where there are lots of broken hydrogen bonds. Now, I should say that those proposals actually at the moment look very unlikely. But the mere fact that they're still being proposed shows how hard it is to pin down exactly what water's structure is like. And it does seem likely that there are genuinely 2 liquid forms of water at high pressures and low temperatures in a sort of under conditions where water isn't any longer the most stable form of H2O, where ice normally forms. So this is actually a difficult idea to test experimentally because it's hard to get into that regime without ice forming. But the idea that's supported by computer models is that if you can get into that regime, you would possibly find the 2 forms of liquid water, one a high density form and one of low density, separating out like oil and water. And it seems that this tension between the more orderly and the more disorderly, the denser, more disorderly networks is what ultimately gives rise to these 2 different liquids. And it's possible that the maximum density at 4 degrees centigrade is an echo of those 2 structures. Now, it's because of these complexities and uncertainties about the liquid state of water that it remains so easy and so tempting to invoke explanations for weird and perhaps pathological properties of water that involve water structure. And that's precisely what Jacques Benveniste was trying to do. Because water was known to form this extended 3-dimensional hydrogen-bonded network, he wanted to imply that maybe this network could somehow freeze around a biological molecule and retain an imprint of its shape, a shape that might hold the key to its biological activity. But sadly, that idea makes no sense. For one thing, it's hard to see why a mold should behave like the object it's molded around. It's a negative imprint, not a replica. But in any case, we know that, as I say, the network is highly dynamic, that bonds are constantly being made and broken in a picosecond. So there's no real reason at all why one should see any long-lived structures of that sort. Nevertheless, water structure in some form or another remains a kind of deus ex machina for explaining various unusual physical and biological phenomena, often, it has to be said, with something like an air of desperation. Now, this kind of idea is particularly notorious in biology, in water's roles in biology, and specifically the question of what water behaves and looks like inside living cells. And that has been and remains a very contentious area. On the one hand, many biochemistry textbooks tend to regard water just as the backdrop of life, and they'll acknowledge that the water is crucial. For example, protein molecules wouldn't be able to retain their shape and their flexibility without it. But they portray water as just a uniform solvent. They describe this 3-dimensional hydrogen-bonded network and then just leave it at that. And biological molecules are frequently, in fact generally, depicted something like this, as though they're sort of floating around in a vacuum, nothing around them, which is necessary in order to preserve the clarity of what you're seeing, but tends to encourage the notion that these molecules would look like this, whether or not there was any water around. At best, the cell tends to be treated as though it's a bag of highly dilute substances. Now, on the other hand, it's been suggested that water in cells is fundamentally different from that in a cup of water, and that this difference is essential for the health of the cell. So there have been claims that water in the cell is more sluggish, and that the more it becomes like ordinary water, the more diseased the cell becomes. That water in cancer cells is more like ordinary water. And the notion here is that the cell somehow tames ordinary water by altering its ordinary structure and rendering it biophilic. And this idea goes back a long way. The Nobel laureate biologist Albert Szent-Györgyi, who coined the phrase the matrix of life to describe water, talked about the structuring of water in cells in the 1950s, and others have talked about the possibility that water forms layered structures on the surface of proteins. Now, the fact is that neither of these ideas, that water is like any other water in the cell, or that water is somehow fundamentally altered throughout the cell, neither of those seems to be right. The truth is more complicated, but also much more interesting. It seems that the structure and properties of water inside cells are altered in many small, subtle and exquisite ways by biomolecules, as well as by other components of the cytoplasm, such as salts, but that this happens only locally, only over short distances. And in this way, water seems able to adjust itself to the presence of biomolecules and vice versa. And it's this delicate interplay between them that makes life possible. And I want to try to give you a little glimpse of some of the ways in which that happens. First, let's have a look inside the cell. Here's what it looks like. And so this is a scale drawing of just a typical bit of cytoplasm, the watery environment of cells with all the biomolecules swimming around. And the first thing that you can see is that it's very crowded in there. In fact, it's even worse than this, because this picture mostly leaves out the small molecules like sugars and so on that are actually there. Those have been put in the top corner. So it's a very crowded place. And on average, you can estimate that the big molecules here, the proteins and so on, are typically separated from one another by a distance of maybe no more than a nanometer or so, so a millionth of a millimeter. And that allows room for no more than 3 or 4 layers of water between them. So it's likely that just about all of the water here feels the presence of the dissolved biomolecules in some way. And the question is what that feeling does to the water. Now, there's no single or simple answer to that. But one of the key questions is what water close to the surfaces of these big molecules looks like. The surfaces of proteins are very chemically diverse. Some bits are covered with water-soluble chemical groups, like bits that can engage in hydrogen bonding, or bits that have electrical charge, like salts. And these are called hydrophilic or water-loving. Other parts have a fatty or oily chemical constitution, and these are called hydrophobic, water-fearing. Here's an image of a typical protein where the hydrophilic and the hydrophobic parts have been denoted in blue and red, respectively. And the deeper the colour, the more hydrophilic or hydrophobic they are. The white bits are neutral in that respect. And the question is if really, and how water structure is altered next to surfaces like this, next to the hydrophilic and the hydrophobic parts. And also, if there is such an alteration in structure, how far does it extend into the liquid and what effect does it have? And this is what's still being debated. One thing's clear, though. There's something about water that encourages the hydrophobic parts, the water-fearing parts, to stick together. In effect, this means that globules of oily or fatty materials in water will come together and stick together spontaneously. Now, this happens at large scales too. And in fact, very recently, it's been discovered that fire ants exploit this effect by clustering together. They have slightly sort of hydrophilic surfaces, and they cluster together on the surface of water to form these hydrophobic rafts, which allow them to float, and by that means to avoid drowning in floods. Now, At the scale of protein molecules, the attraction of hydrophobic surfaces in water helps proteins to aggregate together to form complex functional assemblies of several molecules. It also enables individual proteins to acquire and hold their very particular three-dimensional shapes that they need in order to work as enzymes. So proteins are basically chains, folded up chains of amino acids. This is all one continuous chain folded up in various ways. And typically, these contain some hydrophobic portions of the chain that tend to get packed away in the interior where they're protected from water. Now, that makes intuitive sense that that would happen. But what actually drives this apparent attraction between hydrophobic surfaces? Well, the textbook answer to that relies on an idea proposed in 1945, which says that water next to a hydrophobic particle becomes more orderly, more like ice. You have this picture on the right. And this enables water, the idea is it enables water to arrange itself in a way that minimizes the loss of hydrogen bonds where the water ends and the hydrophobic surface begins. So the idea is that that a hydrophobic particle builds a little iceberg around itself. And in 1959, the biochemist Walter Kautzmann suggested how this might result in an attraction, because as two of these particles come together, this sort of coating of ordered water, these coatings overlap, and some of that ordered water gets kicked out and liberated and becomes disorderly again. And that means there's a gain in entropy, which means that makes the process favourable. So according to Kautzmann's explanation, this hydrophobic attraction is driven by entropy. Now, the problem with this model is that it now seems that there's no good evidence that it's right, and pretty good reason to believe that it's actually wrong. Because it seems very unlikely that water really does form this sort of more orderly structures around hydrophobic surfaces. It may well have a different structure from the one in bulk, probably does, but it's not like, it seems it's not like a layer of ice. In fact, it seems that right next to hydrophobic particles, so here's one, there is probably a very thin layer that contains hardly any water at all. There's a sort of gas-like layer. Now, one recent explanation for this attraction of hydrophobic surfaces is that when they come together, there comes a point, if they're surrounded by a very thin gas-like layer like this, when they come together, there's a point at which the remaining water in between just suddenly all evaporates. And this effect is called capillary evaporation, and it's well known in principle. It means, in effect, that the boiling point of water between these surfaces is altered from what it is for bulk water, and so it all just evaporates. And when that happens, the two menisci at the ends act to pull by surface tension. They pull the surfaces together. And for obvious reasons, this is called a de-wetting transition. And the theory predicts that it might be common between two hydrophobic surfaces when they are perhaps just a nanometer or so in size. And the idea is that this also happens as a protein folds, that de-wetting snaps these hydrophobic regions of the protein chain together. And computer simulations of two hydrophobic plates in water show that you really do see these de-wetting transitions. But it now looks as though de-wetting is probably quite rare as a way of getting hydrophobic surfaces to stick together in proteins. Computer simulations of this small protein called melittin, it's a component of bee venom. It's made up of these four kind of tube-like units that stick together in this barrel shape. And they show that there really does seem to be something like a de-wetting transition, where suddenly all the water molecules in the middle suddenly get spat out and the thing sticks together. But that seems to be quite a rare process. Here's another example that was investigated, a protein called BPHC, where these two fairly flat surfaces come together, these two flat hydrophobic surfaces come together and stick together. And there's no evidence that it all happens in a sudden jump. The water is just expelled gradually as they come together. And it seems, looking at other proteins, that this is probably quite rare. So this attraction generally probably has to have some other origin. Now, as well as helping proteins to hold their shape, water seems to act as a plasticizer. It gives the protein molecule enough flexibility to do its job. If proteins are made too dry, or if they're just taken out of water and put into some other solvent, then they can often fall apart, or they actually remain too rigid to do the work that they normally do. But proteins always seem to retain some water stuck quite firmly to their surface. If you crystallize them, there's a lot of water that gets stuck in there. And it tends to be stuck in very particular places. So here are two structures of water around proteins determined from crystal structures. So the waters stick in these regions. And the waters are these spheres coloured yellow and green and purple. And the different colours denote essentially different layers on the surface. This bound water can therefore be considered an integral part of the biomolecular structure itself. The waters here, the water molecules, are acting a bit like snap-on tools that alter the protein molecule's shape, and they can perform a host of specialized functions. On the one hand, they can act as a kind of removable filler in a protein's cavity, which binds other molecules, to make it somewhat promiscuous about what it will bind to. And that's what seems to happen in a protein called the oligopeptide binding protein, OpA. And that's a protein that's able to grab hold of many little tiny bits of protein, 2 to 5 amino acids long. Pretty much any bit it'll grab hold of. And the idea is that it seems to have this rather big cavity in which water acts as this sort of filler that can be expelled or taken in to fill in all the empty spaces. So it's really as though the water here is acting like little bricks that can be inserted into this cavity to fit the different, I've shown different molecules getting bound here as red, and the blue water fills in the spaces in between. On the other hand, water molecules in very well-defined sites in a protein structure can bridge the gap between the protein surface and the molecule that it's binding, or other parts of the protein, so as to make the protein very selective for a particular shape. Here is I'm showing the catalytically active region in an enzyme called heme oxygenase, and you see that there's a very precisely defined little network of water molecules coloured purple here, and this network acts to transmit and to coordinate movements in the protein chain, in different parts of the protein chain, and that is crucial during the catalytic process. So in effect, they've become part of the protein structure. And if this water cluster is disrupted in some way, then the enzyme can't any longer do its job. So water molecules can be thought of as a bit like little Lego bricks that can be fitted together in certain ways in proteins. And biological molecules mold this Lego-like water into new configurations, new ones that don't necessarily occur in ordinary water. And in particular, narrow channels seem to produce some of the most versatile and widespread of these little water clusters or water structures in biology. So a channel just wide enough to admit water one molecule at a time can be threaded by a chain of water molecules hydrogen bonded to one another. And this is often called a water wire. And the reason it's called that is not just because it's long and thin, but also because, just like a copper wire, it conducts electrical charge. But it does that in a different way from how copper does it. Specifically, these water wires can conduct positively charged hydrogen ions, which are just bare protons. A proton can go very rapidly down a water wire, and that's because it can effectively be shunted from one water molecule to another by just the water molecules turning over and flipping sequentially, and then the proton effectively gets shunted without an actual proton having to travel all the way along the wire. It's just this sort of relay process, and that allows the proton effectively to move very quickly through the water wire. It's a little bit like a Newton's cradle, where the one ball hits at one end and another one pops off at the other. And for this reason, hydrogen ions can move around very fast in liquid water and pure water, because there are these chains in pure water as well, but they're also connected to other bits of the network. But hydrogen ions are often needed in biochemical reactions carried out by enzymes, and several enzymes use water wires to shuttle ions from the solution outside into the middle of the enzyme where the catalysis is happening. For example, something like that happens in the protein bacteriorhodopsin, and this is a protein found in some ancient single-celled photosynthetic organisms called archaea. And bacteriorhodopsin is basically a light-powered proton pump which gets protons to from the inside of the cell to the outside. It pumps them across with light. The light affects the green part of the protein, which is basically a little like the light receptors in your eye, in the pigments in your eyes, and that triggers the release of a proton, which is then sent down a little chain of hydrogen bonded water molecules until it pops out into the outside the cell. And another important class of proteins that contains water channels are aquaporins, and these are molecules that regulate the flow of water itself in and out of cells. So they'll let water through, but they won't let salts or other dissolved substances through. And as such, they act as effectively as molecular water filters for our cells. Aquaporins help our kidneys to process about 180 litres of fluid every day. And because of the way they prevent salt from passing across the membrane with, along with the water that passes, aquaporins are being explored today as possible systems for a sort of biologically based desalination system. But it looks as though we can use the same kind of filtration principle without having to rely on rather delicate aquaporins themselves. One of the most promising approaches that tries to do this uses so-called carbon nanotubes, which are just narrow tubes of about a nanometer or several nanometers wide, which are made from pure carbon. And these are extremely strong, and we're getting very good at making them with just a very narrow range of different diameters. And the idea is that you'll embed these nanotubes into some sort of robust membrane and then drive water through it under pressure, and only the water will go through and the salt will stay out, or other pollutants, in fact. If the nanotubes are narrow enough, less than a nanometer in diameter, then they may be threaded again by just this single chain of water molecules. And the inside of the nanotube is actually rather water repellent, but that turns out to be a good thing. It means that the water can pass through with virtually no friction from the sides at all. So it passes through as though the insides are greased, which in effect they are. What's more, salt, as I say, salt can't get through. Now, salt ions are small enough to actually pass through this tube, but they can't make it when water is restricted to single file. And the reason for that is that the salt ions are surrounded, when they're dissolved in solution, by a cage of water molecules. Because of their charge, they attract water molecules that sort of surround it in this cage. And this, in effect, makes the iron bigger than its real size unless you strip away all of those water molecules first. It's rather like Nicole Kidman trying to get through a doorway. Now, I believe that Nicole can probably get through most doorways, but in practice, that can be tough because she's likely to be surrounded by acolytes and fans and paparazzi, and all of those have to be stripped away before she can actually pass through the doorway, no doubt at considerable energetic cost. And that's the same thing that's happening with these salts. Now, computer simulations of this process show that carbon nanotubes just 8 angstroms across will essentially remove all salt from water, and that slightly wider ones, just a bit bigger than 9 angstroms, will exclude 95% of it. And that would be good enough to make drinking water from seawater. It's been estimated that a membrane 1 square meter made from nanotubes like that should theoretically be able to produce about 1.2 billion litres of fresh water a day. And membranes not very different from those theoretical ones have already been made. For example, a team at Lawrence Livermore National Laboratory in California have made nanotube membranes with where the nanotubes have inner diameters of about 13 to 20 angstroms, and they've embedded them in a strong ceramic matrix and shown that this can prevent up to 98% of the ions from passing through. Now, like narrow nanotubes, aquaporin lets water through, but not salt. But aquaporin is even more clever than that because it also has to block not just salt, but hydrogen ions. Otherwise, it'll upset the acidity balance of cells. Now, I just showed you that actually hydrogen ions go very easily down water wires. So how does aquaporin solve that problem? Well, it seems to do it in clever ways. For one thing, the amino acids in the walls of the pore through which the water threads essentially orient the water molecules by hydrogen bonding. So there's a kind of defect in the wire structure. There's a water molecule oriented sort of back to front so that it can't actually flip and let this proton across. There's also a narrow region of charge in that sort of constriction in the pore, which will repel any hydrogen ion that tries to get through. So between these two mechanisms, it seems that it keeps hydrogen ions out. And nature has other clever tricks for controlling the flow of water through pores. Here's one. This is another protein that embeds itself in membranes. It's called MSCS. It appears in some bacteria, and it controls the passage of ions through cell membranes. And the way it does this is by distortion, by very small mechanical distortions of the pore, which slightly change the width of this neck. So this is a channel for ions that get switched on and off by mechanical deformations of the membrane. And what happens is that if there's a very small decrease in the width of the pore, then suddenly it empties. And once it's empty, then no ions can get through. So researchers are now starting to wonder whether this sort of behavior also can be mimicked in smart water filtration membranes, say by adding chemical groups to carbon nanotubes to act as gates and switches and valves. So I hope I've given you some idea why water is not just life's matrix in the sense of being this passive backdrop on which the tapestry of life unfolds. Rather, it's a biomolecule in its own right, albeit an extremely complex one that can engage in many different processes and can form a kind of versatile, loose macromolecule, giant molecule that interacts with proteins and nucleic acids and membranes and other biological materials. That idea, I think, casts a new light on the question of whether water is essential for life. And that's a question that is explored in this recent book published by Taylor and Francis. If we assume that all chemical processes complex enough to qualify as life will require the kinds of characteristics that we see in protein interactions, then it's hard to come up with any other solvent that seems likely to be able to support such things. Many of the properties that water plays in life do seem to depend to a greater or lesser degree on the special attributes of the H2O molecule itself. In particular, its capacity to engage in this directional, weak hydrogen bonding that allows for reorientation and reconfiguration of discrete and identifiable three-dimensional structures. So while it seems entirely possible that some of water's functions in biology are just those of any generic solvent, rather than being unique to water itself, it's very hard to come up with any other solvent that could fulfill all of the roles that water plays. But that's not the same as saying that water must be essential for life, that all life must be aqueous, because it's not obvious that any one of those roles that water plays in biology is essential for any form of life. It's certainly possible to imagine and even to make artificial chemical systems that engage in some form of information transfer. That's the thing that's indispensable for Darwinian, for inheritance and Darwinian evolution, and transfer of information that allows replication. That there are systems that can do that in non-aqueous liquids. And in fact, life in water has some drawbacks as well, perhaps most noticeably. Water is quite a reactive substance. It has a tendency to split apart the building blocks of these giant molecules of life, like proteins and carbohydrates. So while NASA has chosen to look for habitability in extraterrestrial worlds by following the water, as it puts it, the astrobiologist Chris Chyba has rightly warned that we ought to beware the hydrocentric. We should be wary, for some arguments, that water is indispensable for life anywhere. There are plenty of other candidate solvents that we might imagine life appearing in, provided that we're not too parochial about insisting that life has to be made from proteins and nucleic acids. And here are some of them. How about ammonia, for example, which is around on Jupiter? Or sulfuric acid, liquid sulfuric acid on Venus? Or formamide, which is likely to be quite a common molecule in the cosmos? Or liquid methane on Saturn's moon Titan? Or, going even more exotic, supercritical hydrogen acts as a solvent, and that exists in all probability on Jupiter and in the gas giant planet. Or even gas phases. Fred Hoyle explored gas phase life in his old novel, I think from the 1960s, The Black Cloud. Now, of course, the problem here is that we don't know how to delimit what is life and what isn't, or even whether that's a meaningful scientific question. But in thinking about non-aqueous astrobiological solvents, a review of water's roles in terrestrial biochemistry surely raises one consideration straight away. It's not sufficient to imagine a clear separation between the molecular machinery of life and the solvent that it's in. For water, there's a two-way exchange of behavior and information between them. And this literally erases any dividing line between the biological components and their environment. Water is an extraordinarily responsive and sympathetic solvent, as well as being far more than just merely a solvent. And if any living system is going to depend on that sort of exchange, so for example, that molecular information can be transmitted beyond the boundaries of the molecules that embody it, then it's tempting to conclude that it really would have to make use of water. Now, at the moment, these are, of course, strictly hypothetical questions. There are two ways that they might become more than that. One is that we might begin to explore in detail the surfaces of some of these exotic worlds. And in fact, we've done that, of course. The Cassini-Huygens mission that reached Saturn and Titan in 2004 took some stunning images of Titan's surface. Those are on the left, needless to say. The one on the right is a rather fanciful reconstruction of what these hydrocarbon lakes might look like on Titan. And there's a joint NASA and ESA mission planned to Jupiter and its icy moons. And in particular, it's going to be very interesting to look at Europa, which is believed to have a liquid ocean, a salty liquid ocean underneath its icy surface. And that's slated for 2020. We've now, of course, accumulated a list of over 500 possible extrasolar planets, so planets around other stars. And that's starting to give us some notion of just what an extraordinarily wide variety of worlds might exist in the universe. But the other option is that with the advent of synthetic biology, we might begin to imagine constructing lifelike entities in the lab that can exist in solvents other than water. Personally, I'm agnostic about whether life could be feasible without water, but we can at least say for sure that every life form that we currently know of has reason to be thankful that water is weird. Thank you very much.
Okay, thank you very much, Philip. Thank you very much. We've got a little bit of time now available for questions. There are two people who are going to walk around with the roving mics. Just to remind people, we are being filmed for the webcast at the moment. So could I ask for you to wait till you have a mic if you've got a question. Just introduce yourself and any affiliation that you'd like to mention, and just try and ask fairly clear questions to Philip. Okay? Have we got any volunteers to kick us off?
My name is Raymond Bonnet and I'm from Queen Mary University of London. Can you say something about water as a reactant in biology?
Yes, well, that's thank you for raising that point. It's another of water's roles, because, as I say, water is a reactive compound, and there are plenty of enzymes, plenty of biological systems where water isn't just there as a structural component, but it's actually doing something. It's hydrolyzing a bond. It's providing a source of protons. Um, I mean, there are examples that we can sort of that I could look into, but I don't think I have any easily to hand. But exactly, that's another of water's roles, and very often in molecules like that, one sees that the water has to be the access of the water to the reaction center has to be quite carefully controlled. That reactivity of water has to be delicately handled, and that's a key part of the process. So the structure is set up so that water is carefully sort of marshaled into the site and sometimes kicked out immediately after it's sort of done its role, after it's acted as a reactant. So yeah, again, that's another of its roles.
Sorry, Philip, may I?
Hello, my name is Chris Corton. I'm a chemistry teacher. You mentioned earlier about scaling kettles. Is there any evidence that magnetism can remove scale from pipes?
All I have to go on is anecdotal. I'm not aware of. I mean, I'm sure there has been research on that. I simply don't know of it. Some people here might do. All I know is that some very respected chemists at UCL, who I won't name, although there's maybe no shame in them saying this, have sworn that that it does that this does seem to have some effect. I've never tried it myself. I don't know whether anyone knows anything more about that. You might do yourself, Simon.
Yes, this is one I have to own up to knowing a little bit about. We did some work maybe 10 years ago on and off looking at these claims of whether or not kind of household magnetic treatment devices or industrial scale magnetic treatment devices would actually stop calcium carbonate scaling. The results are incredibly mixed in terms of what you are. But we did actually do some work on a very, very controlled experiment where we looked at in situ magnetic fields on precipitation, and that gave some positive results, but under incredibly well-controlled conditions. Nowhere near what you would find in a domestic unit for treating water.
Right, thanks. Okay.
Yes, hello, thank you. My name is Jeff Bignold. I'm a member of the International Association for the Properties of Water and Steam. I found the whole lecture absolutely fascinating, and it's something that takes a lot of the considerations that IAPS has in terms of steam tables and all the other carefully documented and precisely measured properties to a new level. I think it's very important work. There hasn't been an international association conference in this country, an international, they hold them every 4 or 5 years, for I think 25 years or more. But in 2 years' time, they are planning, the International Association for the Properties of Water and Steam are planning a conference in this country on the International Water ICTPWS, International Conference on the Properties of Water and Steam. I do hope that you'll be able to attend and to stimulate us in such a fascinating way. Thank you very much.
Well, thank you. That's it's a strange community. In fact, it's many communities of people who work on water. There are certainly conferences worldwide that look at the properties of water, but what exactly that means, means different things to different people. If you're a chemical engineer, You know, it means one thing if you're a molecular biologist, it means quite another. But I think, you know, what's interesting to me is that probably at root, the same issues, the same fundamental issues are involved. You know, what water does around dissolved ions or close to surfaces, you know, is crucial to both corrosion and to membrane proteins. So yeah, that's what I'd say.
Just a further supplement. You were talking about chemistry in cells where there's very little space for the water. Again, spreading it to a different concern, you're talking about very low Reynolds numbers. And again, when you compare aerodynamics with very low Reynolds numbers, the properties change immensely. And that's just another factor to take into account.
Yeah, thank you. I haven't really said anything about hydrodynamics, and that's a hugely interesting, important area. And questions like what water structurally looks like close to different kinds of surface have extremely important consequences, of course, for the slip behavior next to the surface, and you know how water flows. So yeah, thank you again for raising that. That's another important, and again, actually another controversial area of how water behaves.
Sorry, Philip, may I ask you a question? I just want to ask you, you mentioned a bit about biodesalination. It's been hot for the last 6 to 7 weeks in the UK. Lovely, great for my holidays. And but it's going to lead to lots of press and lots of interest about water shortages here in the UK. We've seen it in Australia. We're obviously aware of it in sub-Saharan Africa and elsewhere in the world. And desalination is talked of as, you know, one of the kind of key techniques or key processes for the future here. At the moment, it's incredibly expensive, you know, relative to other treatment processes. I mean, how you mentioned the carbon nanotubes, but also the biodesalination work you mentioned on. I mean, have you got any feel for, you know, how long that may be taking, whether or not it does offer real kind of alternatives to what's currently, you know, pushing water through a very dense membrane?
Yeah, well, I think it does. I'm quite optimistic about that. I mean, there's a company in Norway that is aiming to develop aquaporins for desalination. I'm not quite sure. I mean, I know that they're hoping to commercialize something fairly soon, but I'm not quite sure where that stands. By fairly soon, I mean, you know, a few years. And I think the carbon nanotube stuff has progressed very quickly. I wouldn't be at all surprised if that turns out to be one of the areas in which, if you like, you know, nanotechnology or carbon nanotechnology first makes an impact. Because, you know, as I say, these membranes have been made, they've been shown to work to some degree. It's, you know, the rest, and of course it's a big rest, is engineering. So, yeah, you know, I think that's looking like a real alternative at the moment.
I'm Jebel Green. I'm a retired food chemist, and I'm here solely out of interest. I found your talk fascinating, but in the course of it, you never mentioned water in its gaseous state. Does it behave like the other hydrides of the lower molecular elements?
Water, yeah, the question was whether water in its gaseous state behaves like the other hydrides. I mean, it's... I know less about it actually, except to say that I believe that it does. Water can form. It continues to have the capacity to form small gas phase clusters, and those have been, you know, they're very interesting in themselves. They've been studied extensively to see what sort of shapes they can form. You know, whether they're sort of like little bits of liquid water, or whether they form different structures. But you know, if it's completely dissociated, then you know, as far as I'm aware, it is more or less like another hydride. But again, I mean, Simon, you probably know again more about, or others of you, will know more about steam and gaseous water than I will.
Oh, Jim Mackenzie, I'm self-employed, semi-retired. I've worked in the water treatment industry for about 30 years. And I've been around very many sites. And over the last 15 years, I've seen more and more magnets fitted to incoming mains, mostly in government buildings. Is the government wasting my tax?
It sounds like it from what Simon says, and yeah, I hesitate to add any more to that. I mean, it's except to say, you know, I just find it an interesting phenomenon. Of course, there are also claims that magnets have biological effects, and that, you know, somehow this is being mediated through water. Um, it's just a, you know, it's just a minefield really when you start looking into some of these claims. I think particularly because, you know, there's often just enough plausibility there, but also any effects that you might see are completely on the margins, are hard to reproduce. You know, I have to say that even when Nature sent this team to investigate Benveniste results, what they found wasn't absolutely clear cut. They didn't just find that there was no biological activity at all once you diluted beyond a certain point, which is what you'd expect. They found, according to the assay that was being used, they found that, you know, sometimes things did seem to happen. And the same was found. A team at UCL some years later conducted a very thorough study to try to, you know, to pin this down, and they found the same thing, that actually activity didn't completely go away. It was never reproducible. It was never, you know, so there was nothing you could easily explain, but there was something strange going on, and it sounds as though, you know, with magnets it may be similar.
Well, if we don't have any final questions, I think maybe we could just thank Philip again for his time and superb talk.
Thank you.